Hello everybody, my name is Héctor del Castillo and I'm a PhD student of the Pontificia Universidad Católica de Valparaíso, Chile. Now let's begin with the mathematical discussion. The poster is about the Langlands Functoriality Conjecture, a main part of the Langlands program. It was already expressed in one of the starting points of this program, the letter of Langlands to Vail, that shape a whole area of mathematical research, as stated in the 2018 Abel Prize webpage. Since then, there has been different approaches to prove that conjecture. We will follow the path traced by Cogdell, Kim, Petitke-Shapiro, and Shahidi over number fields and Lomeli over function field to prove the generic Langlands Functoriality Conjecture for SO2n star in the function field case. We begin by introducing some notations. We let F be a global field or a local field of positive characteristic. Whenever F is a global field, we denote by F between bars the set of places of F, by Fx the completion at a place X, and by Qf, or simply by Q, the cardinality of each field of constants. We also denote the ring of adels of F by AF. Now we start with the first ingredient for the functoriality, the quasi-split even special orthogonal group. First, we define the orthogonal group. The orthogonal group, OQ, of a F quadratic space VQ is a closed subscheme of GLV, which represents the functor of invertible linear operator respecting the quadratic form Q. If the vector space V is even-dimensional, the special orthogonal group SOQ is defined as the kernel of the Dixon morphism. We use this definition to avoid some problem in characteristic 2 case. It is connected, smooth, and its center is the 2 root of unity. Finally, the Dixon morphism DQ is a smooth surjection identifying the constant group of integers modulo 2 with OQ modulo SOQ. We will consider the following family of quadratic spaces. For a separable quadratic extension E over F and n greater than 1, we let Q En be the quadratic space given by Fn minus 1 times E times Fn minus 1, and where the quadratic form is given with the following formula. Here n E over F is the norm map of E over F. Okay? To simplify the notation, when the base field F is clear from the context, we denote by SO2n star the special orthogonal group of QEn. Now we start with the second ingredient for the functoriality, the L group and the Satake parametrization. First, we start with the dual group. The dual group of the F group SO2n star is the split expression orthogonal group SO2n over the complex number C. This group is defined from some combinatorial data of SO2n star. Now, as the group SO2n star is non-split, we have a natural non-trivial action of the Galois group, given in the following way. With this action, we thus have that the L group of SO2n star is the semi-direct product of SO2n of the C point of SO2n and the Galois group F between these two groups. Okay. Now, in the case where G is either SO2N or GLM over F, the dual group G hat is SO2N or GLN over C respectively, and the action is trivial as they are split groups. We thus in this case obtain that the L group of these groups is given just by the direct product. The L group of Fx groups will codify certain local representation theoretic information. There is a bijection called a Satake parametrization between unramified and semi-simple conjugacy classes of the L group. The corresponding semi-simple conjugacy class associated to an unramified representation pi x of GLM fx or SO2n star fx will be denoted by C pi x. Now we have the two ingredients for the functoriality. Let root 2n star be the following L group homomorphism. Let pi be a cuspidal automorphic representation of SO2n star AF, unramified outside a finite subset S of places. A Wycliffe or a transfer of pi is an automorphic representation big pi of GL2n AF, such that the representation big pi x is unramified for every x not in S, and that its semi-simple conjugacy class C big pi x satisfies the following formula for every x not in S. Now we are ready to state the first result of the poster. Let pi be a globally generic cuspidal automorphic representation of SO2n star AF. Then there exists a transfer big pi of pi. In this term, we assume this condition of being globally generic. That means that there is some notion of Fourier coefficient doesn't vanish. Okay, this hypothesis will be crucial. We will see later where we use this hypothesis. But now, let me remark that our case study the quasi-split non-split group SO2n star, which complements the work of Lomelí for the split classical group SO2n. The proof follows closely the work on the functoriality conjecture of Cogdell, Kim, Piatetsky, Shapiro, and Shahidi over number fields, and Lomelí over function fields. As them, we use as a starting point the converse theorem to translate the existence of an automorphic representation big pi of GL2AF to the existence of an admissible representation of GL2AF with the right property on its L functions. So now we first present the L function, and then we will describe the properties needed for this translation, the converse theorem. In order to define the L functions, first we want to start with a local construction. From a pair of local irreducible smooth representation of the general linear group and a character Cx of fx, one construct the local ranking server factors, the L functions, the epsilon factors, and the gamma factors. This lie in this field. Then from this one we can construct the global function. So let pi and pi prime be admissible or reducible representation of GLN-AF and of GLM-AF respectively. We then, using the local L function, we define as a Lerner product the global L function and the global epsilon factor. Now we start state the converse theorem that will allow us to translate the condition of finding an automorphic representation to find a admissible representation with the right properties on the L functions. So let n be greater than 2, and let pi be an irreducible admissible representation of GLN AF, and eta be a smooth character of the ideals trivial on the invertible element of F. We suppose that for a finite subset S of places, pi satisfies the following properties. The first one is that the central character of pi is trivial on the invertible element of F. The second one is that for all pi in the set of twisted by eta cuspidal automorphic representation of GLR with r greater than 1 and less than n minus 1 unramified at every x in S, the formal power series in q to the minus s, these L functions, are actually polynomials, and they satisfy the functional equation. So with these two properties, then the converse theorem states that there exists an irreducible automorphic representation ρ of GL and AF such that for each place x not in S, such that Px is unramified, rho x is unramified, and pi x is isomorphic to rho x. Next, the tool that will allow us to establish the desired property of the L function is provided by the Langlands method. This method provides us with a theory of L functions in the following situation. Let pi be a globally generic cuspidal automorphic representation of SO2n star AF, and tau be a cuspidal automorphic representation of GLM AF. Note that here we use the hypothesis on pi, the globally generic hypothesis. Then there exists a global L function and an epsilon factors. The L functions are rational functions on q to the minus s, and they satisfy the functional equation. Now let me explain the strategy of the proof of the theorem. First, one give a construction of a candidate leaf big pi prime. At the unramified places, we use a Take parametrization. At the ramified place, we twist our representation by a sufficiently ramified character eta x so that the L functions of pi x is the L function of a simple representation. This is achieved thanks to an important stability result on the gamma factors due to GAN Lomelí. Now, for this simple representation, one can explicitly find the candidate big pi prime x. Moreover, we can also check that for a character eta sufficiently ramified at x in S, we have the following relation between L function and epsilon factors for every tau in this set. And that also the central character is the quadratic character of the ideals defining E. Okay, so with these two properties we have the condition that the central character is trivial on the invertible element of F, and also thanks to the Langlands method, the property of the functional equation of the L functions. So what we are left to to check is the polynomial condition on these L functions. And for that one, use further property of the Langlands-Shahidi method to obtain that. Now that we have our transfer, we would like to know a little bit more about it. First, we recall that every automorphic representation big pi of GL to n arises as a subquotient of an induced representation where pi I is a cuspidal automorphic representation of GL ni. With this, the next result of the poster is the following. Let pi be a globally generic cuspidal automorphic representation of SO2n star AF. Then, as we know, pi transfer to a globally generic irreducible automorphic representation big pi of GL2n AF. Moreover, big pi is an isobaric sum, a special subquotient of an induced representation as above, where each pi I is a unitary self-dual cuspidal automorphic representation of GL ni AF, and they are distinct from each other. An interesting application of the last result is the following result. It's the so-called unramified Ramanujan conjecture. So let pi be a globally generic cuspidal automorphic representation of SO2n star AF. If pi I is unramified, then its attack parameter has absolute value 1. This is a consequence of the previous result and the Ramanujan conjecture for general linear group, because the isobaric terms pi i's are unitary and cuspidal. Thus, its local components are tempered. So that's all for now, and thank you for your attention, and see you in the conference. Bye.